Hello everyone. For this week's tutorial, I'd like to discuss rectangular versus polar form of vectors, and how polar form is often better used for multiplication and division because it makes it more clearer than in rectangular form. And similarly, how rectangular form makes addition and subtraction more clearer, as demonstrated last week. If you can recall from last week's tutorial, rectangular form looks like the individual components, the x, y components if it's 2D, or x, y, and z if it's 3D, all grouped separately with commas, and the group indicated with a bracket, like this. And adding and subtracting vectors in this form is as simple as adding and subtracting the individual components. However, the other form is called polar form, and also uses entries separated by commas and grouped within brackets. But the actual entries themselves are different. In particular, for a 2D, you have magnitude and angle. And for 3D, you have magnitude, XY angle, which is the 2D angle, and this, which is used to represent a special 3D angle along the YZ axis. And is called phi, spelled PHI, which is a Greek letter, like the famous pi from geometry. Now that we have discussed how the formats of polar and rectangular forms work, we can discuss how to convert between the two. To convert from rectangular to polar form, you simply apply the formulas discussed in the first lesson on vectors, which, to recap, is magnitude squared equals x squared plus y squared, and theta is inverse tangent of y over x, making sure to add 180 if your angle happens to be between 180 and 360. And 3D magnitude is x squared plus y squared plus z squared square root. Theta is the same as in 2D. And phi is inverse tangent of z divided by x squared plus y squared. Or more simply put, v is inverse tangent of z divided by 2D magnitude. And making sure to add 180 if your degree happens to be between 180 and 360. Converting from polar form back to rectangular form can be thought of as breaking this down. And the exact formulas would be x equals magnitude times cosine of theta, y equals magnitude times sine of theta, which works for both 2D and 3D vectors, and z equals magnitude times sine of phi for 3D vectors specifically. Now that we have discussed how to specifically convert between the two forms, I can demonstrate multiplication and division using polar form. While vector addition and subtraction is simply adding and subtracting all the components, vector multiplication and division is slightly more complicated. In particular, the magnitudes are multiplied, but the angles are added instead, even though you are multiplying vectors. Just like how division is the opposite of multiplication with regular numbers, the same exact logic applies to vectors. So you divide the magnitudes, but you subtract the angles instead. Visualizing this graphically, multiplication would look something like this. And dividing the 90 degree by the 0 degree would look something like this. We can also graphically demonstrate without using zero angle vectors as a way to reinforce the understanding. So multiplying a 45 and a 180 degree would look like this. And dividing the 180 by the 45 degree would look like this. "3D multiplication is a separate and even more involved process and is called the cross product. The method I have shown you now with the 2D vectors is called the dot product. However, I'd like to take a break from discussing the math formulas for the next couple of tutorials. Now that we have a grasp of the basics of vectors and how to work with them, and start delving into real-world physics problems and how vector math applies to them, such as friction, inertia, momentum, and so much more.